I am Buhle Tagalashe, a Chief Engineer in the Pyrometallurgy Division at Mintech, and I'll be chairing this webinar. Thanks to all the attendees from all over the world for joining in this morning here in South Africa and afternoon in Australia. I would like to take this opportunity to introduce today's speaker, Professor Peter Hayes, who is an expert in pyrometallurgy. His inspiring career spans for many decades. He's a professor of metallurgical engineering at the University of Queensland in Brisbane, Australia. Professor Hayes was the founding director of the Pyrometallurgy Innovation Center, the PyroSearch, at the University of Queensland. He is an author of the book entitled Process Principles in Minerals and Materials Production, now in its 4th edition. He has published over 400 research articles in journals, national and international conferences. His research interests include high temperature phase equilibria and the kinetics and mechanisms of reactions. Ladies and gentlemen, this brings me to today's talk. It is entitled Kinetics of Pyrometallurgical Processes. It should go faster, shouldn't it? This is of course of importance both from the fundamentals point of view and for applications in the commercial production and refining of metals. Two features that make the use of high temperature processing attractive for applications in the commercial production and refining of metals are the high specific rates of production and the rapid approach to chemical equilibrium. Both chemical reactions and diffusive mass transfer rates are thermally activated processes. And this naturally leads to the assumption that by increasing processing temperature will result in increased production rates. It turns out that in practice, this is not always the case. In this webinar, we explore some case studies and examine possible reasons for this unexpected phenomena. And ladies and gentlemen, kindly note that this webinar will be recorded, and please ask your questions under the Q&A tab at the bottom. And this will be addressed at the end of the presentation. And before I hand over to Professor Hayes, I would like to give this opportunity to Dr. Stuart Nicole of the Oxide to say a few words. And over to you, Stuart.
Oh, thanks. So from the OSIM side, I would first like to thank the South African Institute of Mining and Metallurgy for hosting this first webinar in this collaborative series. I'd also like to thank Peter for sharing his passion and joy for metallurgy and his drive to share with others, and his assistance in setting up this collaborative webinar series. So the OSIM looks forward to not only hearing from Peter today, but hearing from other South African experts in the minerals industry. We're hoping that our members are able to apply some of the learnings from another side of the world to their work, and we hope that the South African Institute of Mining and Metallurgy members enjoy hearing from experts from our side of the world. So we look forward to hosting the next webinar in the collaborative series. So I guess I'll hand over to Peter.
Hello, everybody. So thank you for joining me for this webinar. I hope to stimulate some thinking today about what's happening in your processes, in your production, and to question what's really going on there and how we can make it better. And I want to show you some examples of things that have come across in my research which might stimulate some of that thinking. So first I'll go to sharing my screen and I'll just get this presentation set up. Okay, well, let me first start by thanking the South African Institute of Mining Metallurgy and OSIM for hosting this webinar. And I've chosen this title, it's a bit provocative, and I want to stimulate your thoughts about what's going on. There are not going to be too many equations in this presentation, so you don't need to keep your notepad handy to write down those equations. So it's not that sort of presentation. It's more about looking at the evidence and understanding what the evidence is telling you as we go through the story. So I realize that we have people listening in who have a range of backgrounds and experiences. So the first few slides are going to be more of an introductory nature to get us started. And then I'm going to show you some examples of some systems where things happen which we didn't expect. And what can we learn from that? So, as metallurgical engineers, we generally push to make reactions go faster. The general manager always wants to increase productivity because that means more profitability for the plant. And through our training as metallurgical engineers, we know that some of the key process variables we have to play with are composition, temperature, pressure. I'm going to be focusing on pyrometallurgical examples, but I hope that some of the things I'm going to say are going to be also applicable to hydrometallurgical systems as well, and other types of systems. So I want to start by taking those key process variables, the three of them, composition, temperature, and pressure, and realizing the first thing to come to mind is that it influences the thermodynamic driving force for chemical processes and chemical changes. So when we're examining different processes, we have to appreciate how close we are to the equilibrium to start with before we can then link that to how fast we might expect it to go. The two are not independent of each other. So we need to understand the driving force. And I want to show you some couple of examples of how that how we can look at that and examine and take away some learnings from that. I'll start with a very simple system, the iron oxide system. And here we're trying to remove the oxygen from the association with the iron. And there's two principal ways in which we can do that in industrial practice. We're using hydrogen or CO gas as the reactant gas to pick up the oxygen and change it to H2O or CO2. So I want to just, from a thermodynamic perspective, just compare the behavior of those two systems and how that influences, or how those process variables can change the thermodynamic driving force for the reaction. So let's look at this very simple diagram with temperature on the vertical scale and gas composition on the horizontal. So the left-hand side here represents pure hydrogen or pure CO, that is the reactant species, and the right-hand side over here at 1.0 represents when the gas phase has only steam, H2O, or CO2. So this particular system is at 1 bar total pressure and the carbon activity at 1 here. Let's just look briefly at the phase boundaries here for iron and iron oxide. So let's first start with this dotted line. This represents the boundary between metallic iron and iron oxide in the form of wustite, this Fe1-XO, and magnetite, Fe3O4, which is stable at the lower temperature. So you see that as we go up in temperature, the equilibrium between iron and FeO, that is the critical condition for reduction, changes with temperature. And similarly, we can look at this full line here. This represents the line for the CO-CO2 system. So at low temperatures, we see that the equilibrium between iron and, in this case, magnetite is almost constant with temperature. It doesn't change very much until we get up to this triple point here. And then we see the reaction requiring more CO in order to reduce the iron oxide. So if we look at a particular ratio of reactant gas, hydrogen to H2O or CO to CO2, marked by this red line, you can see that we have to get up, if we go up to 850 degrees centigrade, it doesn't matter which system we're using, H2H2O or CO-CO2, because both intersect that phase boundary at that composition and that temperature. However, if we see how the system is changing with temperature, you find that at low temperature, you need more hydrogen relative to steam in order to cross this boundary from the magnetite side on the right-hand side to the iron side on the left-hand side of that dotted line. On the other hand, the CO does exactly the reverse. So as we go up in temperature, besides its independence at low temperature, we find that the iron oxide becomes more stable relative to the iron as we go up in temperature. So you can see these lines and the equilibria are going in the opposite direction. So if we're thinking about the driving force for a reaction, we find that for a given composition here, we see that we have no driving force in the case of hydrogen steam until we get to at least 850 degrees centigrade. On the other hand, if we're talking about the CO-CO2 system, we find that the driving force is actually reducing or lowering. That is, the difference between the red line and the phase boundary is decreasing as we go up, and in fact becomes zero at 850 degrees centigrade. And if we want the reaction to proceed, we actually have to add more CO, so depart from this reaction. So you see that just increasing the temperature affects that driving force, which is a critical part to it. And here I'm just repeating that statement. So for a given gas ratio, increasing the reaction temperature increases the thermodynamic driving force for the case of hydrogen steam, but decreases it in the case of CO-CO2. So, and increasing hydrogen steam ratios and CO-CO2 ratios will increase the thermodynamic driving force for reaction in both cases. But what we find is the utilization of the gases will be decreased because we're having to use more of the reductant, and that means increased costs. Okay, so let's try and link that, first of all, that thermodynamic concept to the kinetics of reactions, either movement, mass transfer, or chemical reactions. We know that the mobilities of atoms and the chemical reaction rates increase with increasing reaction temperature. We know this through the Arrhenius equation, which is these mobilities increase in general exponentially with increasing temperature. So we might just say, well, why don't we just increase the temperature? It must go faster because this mobility increases. Well, does that happen? Well, the rate processes are actually a combination of the mobility and the driving force. So it's not one or the other. It's not just the driving force. It's not just the mobility. It's the combination of those. And what you can see from this product is that you can get the reaction going up or down, depending on how we change those individual contributions. Let's just look at a simple example of that. And people who've studied material science in particular would be familiar with these types of relationships. So we're plotting rate on the vertical scale, either rate of nucleation of a new product or the rate of growth as a function of temperature on the horizontal. And this TC, this vertical dotted line, is telling us the critical temperature. So at temperatures above TC, this new product will not appear. There's no thermodynamic driving force for formation. Below that, we see that as we lower the system below that critical temperature, we see the reaction rate or the growth rate actually increases with lowering temperature. So thermodynamic driving force increases. But we get to a maximum here, and if we go to lower temperatures, we find the rate is actually dropping off. So what's happening here? On this side of the equation of the line, we're actually getting, we have high mobility, but the thermodynamic driving force for a reaction is increasing. And so the rate is increasing. When we get to this situation, we find that at lower temperatures, we find that the mobility of the species in the system is decreasing at a faster rate than the increasing driving force. And so overall, the rate will decrease. So is the rate going to increase with temperature or decrease with temperature? If we start from low temperature, we find in this case that the growth rate is increasing up until this critical temperature. And then after that, it actually starts to go down again. So we need to be sure about which side of this growth rate hump, if you like, or maximum we're sitting in our process. The same thing applies to nucleation, which doesn't usually have its peak nucleation rate at the same temperature as the growth rate. So these are usually displaced from this critical temperature by quite a difference. So again, you can see if you're at low temperature, increasing the temperature will increase the nucleation rate. If you're at high temperature, increasing the temperature will decrease the nucleation rate. So not obvious. Now, I want to take you to a case of reduction of nickel oxide. Nickel is in the news at the moment because we're talking about use of nickel in lithium-ion batteries, for example. So this is an example then of how we can make nickel metal from nickel oxide, again using hydrogen and CO, a very simple example. So what do we know about this system? It's heterogeneous, that is, involves a phase boundary, in this case a solid and a gas, and creating a new solid product. It's non-catalytic, so this is not a catalytic reaction, it's a phase transformation or chemical reaction. They couldn't be much simpler than this sort of reaction. So what happens when we look at this type of system in control conditions? These are some measurements of the fractional reduction as a function of time for reduction of nickel oxide in hydrogen. So these are isothermal reaction experiments. And you can see at low temperatures, things are the reaction rate is very low. The slope of this line is very low. Increases as we increase the temperature from 200 up to 500. And well, there's something strange happening here. We find that the rate at 500 is the same as 1000 degrees centigrade. So these guys have increased the temperature 500 degrees more with no benefit at all. That's not what we expect from the Arrhenius equation. What about CO gas? Well, something happening here. As we increase the temperature, the rate goes up, but we find at low temperature, at 700 degrees centigrade, the thing's actually not going at all. Basically, it stopped. So we expect a continuum. Why isn't there a continuum here? Why isn't it slower as we go down? Well, it is slower, but not this. We don't want it to be that slow. Okay, so let's look at the results of what's happening in these systems. And we've done this experiments by putting samples of material in this special apparatus, which allows us to put the sample into the flowing gas stream at controlled temperature, and then quench the sample out of the reaction after a given time. And in this way, we were able to stop the reaction and then look at the reaction interface and see what's actually going on physically. Normally, as pyrometallurgists, we don't have this luxury. Things are inside a big furnace and we can't get inside to observe. But this apparatus allows us to do that by stopping the reaction through quenching it. And we can measure the thickness of the product produced as at different temperatures. So these are isothermal tests done at different times. So the triangles at the bottom are giving us only 5 seconds, whereas the squares at the top, that's 80 seconds. So you can see as time goes on, the thickness will get larger for any particular temperature. But again, we don't see anything that obeys the Arrhenius equation here. As we increase the temperature, the rate increases quite dramatically from 500 to 600 degrees centigrade. But then after that, it actually drops off. 700, 800, 900. And there we're back to that situation where the rate at 500 or 600 is the same as 1000. So we have some other additional evidence to show that this happens in the CO2 system as well as the hydrogen steam system. Here we go, you can see that growth rate as a function of temperature. And this A, B, C, D are different thermodynamic driving forces. So 100% CO is the maximum driving force we can apply to the system. And A is getting close to the equilibrium between nickel and nickel oxide. So it's a low thermodynamic driving force. And what we find is that the rates not only go through this minimum at somewhere around 700, but also depend on the thermodynamic driving force and the partial pressures of the reducing gas. Okay, so let's have a look at some of these microstructures that are formed on the surface of the sample. We're going to start at 600 degrees centigrade, and we're going to examine the surface using a scanning electron microscope. So this enables us to look at very low, so I'm having a problem with my marker here. You see we've got a 10 micron marker here. So this is, we're looking at the surface of a nickel oxide with this line, the horizontal line here is the grain boundary between, and we can see that there are, if you like, little holes appearing on the surface of the nickel oxide. And these are called facets. So what's happening is that the reactant gas is preferentially taking away the oxygen from the surface at certain sites on the surface. So it's not happening uniformly on the surface. There are certain planes which it's easier to take oxygen away from the nickel oxide than others, hence the facety. If we go for a longer time, some strange things happening here. So we see that the surface, which is initially smooth on the right-hand side here, forms these instabilities or holes. So we spontaneously start to decompose the surface. Might get rid of this, change this pointer. Go back to the traditional pointer. We see that the surface, instead of being smooth, like here, it's become, created these holes or instabilities in the surface. And as we go on, these instabilities grow across the surface. You can see one colony over here, another colony here, okay, and some of the faceted holes in the nickel oxide surface there. If we look at 600 with a high CO2 ratio, then we see this is the original surface of the sample. Now we're looking at a cross section. We can see that this instabilities have moved in a reaction front all the way into the dense nickel oxide here. So this is porous nickel and this is dense nickel oxide. If we look closely at that interface, you can see how those pores are created. So essentially spontaneous tunnels are appearing in the surface. So instead of having a nice flat nickel oxide surface as we started, it's become irregular, and these tunnels are actually burrowing their way into the nickel oxide, and the gas is coming from the outer surface of the particle through these connected pores, and you can see how there are some connections here. So these connections go all the way to the surface, and so we have gas diffusion through these pores. If I go up to 700 degrees centigrade, we can see the shapes of the pores have changed slightly, and in this case we've actually cut the sample with a special probe. So we've got a smooth surface here, not a rough surface. We've taken a smooth cross section, and you can see this is the sample surface, and you can see these pores tunneling their way into the nickel oxide. And in some cases, the tunnels have actually bypassed some of the nickel oxide. So you can see there's some nickel oxide encapsulated in a dense nickel layer, which is formed around there. So the gas is going all the way to the nickel oxide interface, but it's being covered by a dense nickel layer over the surface of the pores. If we go to a higher temperature, 800 degrees centigrade, and look at the surface after a very short time, we find the darker gray is the nickel oxide, and these lighter gray islands on the surface are actually nuclei of nickel metal. So we have nucleation of individual nickel metal on the surface, and as time goes on, we find that those dense nickel nuclei grow and eventually seal off the surface here and form a dense nickel layer. So in this case, we actually stop the reaction because the gas can no longer access the nickel oxide underneath. So there's an impervious layer between the gas phase and the dense nickel oxide. Clearly, this is going to have an effect on the rates of reaction because we can't supply the CO directly to the nickel oxide surface. Any reactant has to go through this dense layer. If we change the gas condition, what happens is that we get that initial dense layer, and then it breaks down periodically, and we become porous again. So we call this a discontinuous growth. So this is the original surface, which was covered with dense nickel layer. Then those nickel layer broke down, and we had periodic formation of nickel layer and breakdown as we progress into the sample. Just to show you proof of that, this is at 1000 degrees centigrade at a very short time, and we can see that in this case we formed dense nickel, and what you see here are these round circles. These are the bumps, if you like, which have formed in the surface, and in here we can see holes, which is a bit like mini volcanoes, which have actually burst through and broken the layer down on the surface. And we see this type of reaction happening in the case of iron oxide as well as nickel oxide. And here what happens, so the gas gets separated from the nickel oxide, but carbon can diffuse through the metal layer, react with the nickel oxide and form gas here, and that blisters and eventually bursts that layer and allows the gas to come in, and the whole reaction starts again. So we can make a maps of these different reaction morphologies depending on the reaction temperature and the gas conditions in the reaction system. So here we have CO over CO plus CO2. So in other words, the concentration of CO in the gas mixture. Pure CO at the top, no CO at the bottom. And these various marks here indicate the different types of reaction product that we see. We see that at the low thermodynamic driving forces and low temperatures, we tend to get dense layer of nickel forming. At high thermodynamic driving force, particularly at low temperature, we get a continuous porous microstructure. And at the higher temperatures and the lower driving forces, we tend to get this discontinuous pore growth. So if we can summarize what's going on in this system, you see that we have a region here where dense nickel is formed on the surface of nickel oxide, which, to be honest, is bad news because that stops the reaction completely. At low temperatures, we get the formation of dense nickel carbide. So in this particular system, the thermodynamics tells us that CO reacts with nickel to form nickel carbide at particular CO-CO2 ratio. And so that's why the reaction stopped, because we were forming nickel carbide and not nickel metal. So at that critical range here, we can get porous nickel forming at low temperature. And that forms various structures from what looks like a coupled structure to a cellular structure to a dendritic structure. At high temperature, we have porous discontinuous pattern, which is the formation of a dense layer and then the bursting of that layer. And all the way across the temperature range at low thermodynamic driving force, we get the formation of dense nickel layer. So let's go back to the structures we saw in the nickel oxide hydrogen system, and here's some examples of the microstructures. So here's the dense nickel layer product. You can see stopping the gas getting access to the nickel oxide underneath. Here's the irregular interface formed by the discontinuous growth. So it forms a dense nickel layer, which then breaks down, and we get the pores formed again, and then gets covered again. So a cyclic process is a discontinuous process. So stop, start in here. At the high driving forces and low temperatures, we get this fine porous continuous process where the gas pores go right from the surface of the sample all the way to the nickel oxide interface. So we get gas diffusion all the way there, and the CO2, the reaction product, goes all the way out too. So we have counter diffusion of gases in those fine pores. And at low temperatures, we get a modification of that structure, which I'll explain a bit more about in a minute. Okay, let's take a real case of reduction of nickel oxide and look at what happened in a situation not where we have isothermal tests, but where we have an increasing temperature. So starting off with a basic nickel carbonate, as we go up in temperature, that decomposes into nickel oxide in these very fine granules here. These basic nickel carbonate is formed from a hydrometallurgical process that when we heat them up, these granules change to nickel oxide. Now you can see at low temperature, we've got this very fine porous nickel layer, and you can see some of the traces of the onion rings, if you like, which reflect the decomposition and the precipitation of the basic nickel carbonate. That's the structure there. And we expect that increase in temperature, as we increase the temperature from 600 degrees centigrade in A to 700 degrees centigrade, that should actually go faster. And we should get rid of the remaining nickel oxide. But what do we see? No, we see some nickel oxide trapped in the middle here. So we say, well, let's make it higher temperature, keep going. And what happens at go to higher temperature, 800 degrees centigrade, we still have the nickel oxide. And now we have this surrounded by a dense layer of nickel. So we've got rid of the porous nickel, we have a dense layer of nickel, which has made things worse because that nickel layer's got thicker and impermeable. And at higher temperature, 900 degrees centigrade, then the whole thing starts, the nickel metal starts to sinter together, and we reduce the porosity of the product. So bad news all around. What's happening here? This was taken from an industrial process where we had a continuous heating in a kiln. So as it went down the kiln, it was getting hotter, but we never got a complete removal of the oxygen from the nickel oxide. And nickel oxide, of course, is a carcinogen. So this is a real problem because we have to meet product specifications. So what's going on here? So first, the BNC is converted to nickel oxide. At low temperature, things go swimmingly. So we can reduce the nickel oxide to nickel and get porous nickel. And as the temperature increases, the morphology changes. We start sintering and densifying that porous layer because the pores are very fine, or order of tens and hundreds of nanometers. As the porosity decreases, then the rates of gas diffusion through the product layer decrease and the gas composition changes. So it becomes closer to equilibrium. And so the rates slow down, and eventually we can get a situation where we no longer get a porous nickel reaction. We get the dense nickel. So it becomes limited by solid diffusion of oxygen through the nickel, and then we can only get reduction of the nickel oxide underneath by the discontinuous breakdown mechanism. And unfortunately, what happens then is we get the recrystallization of any remaining porous nickel, and we get the final encapsulation of the nickel oxide with dense nickel product. So increasing the temperature simply doesn't help us. I'll take another example here, the last example, which shows that something strange happens when you have heterogeneous reactions. This is some work by Chapman and et al. From Wollongong, and they were simply looking at the dissolution of carbon, solid carbon, into liquid iron as a function of time. So you can see the concentration of carbon as a function of time. We expecting a fast reaction rate. We expect this to it to slow down as we come to equilibrium, but unfortunately, it slows down and actually stops. So equilibrium is somewhere here around 4% at this temperature. And over here, this is at a higher temperature. I'm sorry, the temperature is missing from here. I think this is about 1450. This is about 1500 or 1550. So a higher equilibrium, but we don't get there because the reaction actually stops. So what's actually happening? Well, again, look at the interface. And we see that the coke here in the black is separated from the iron. And this is a solidified iron, graphitic gray iron. You can see the graphite flakes, carbon flakes in the iron. And in between the coke and the iron, which was liquid at temperature, we formed a dense layer of a mineral which contains calcium and alumina. Where did that come from? Where did that come from? Nobody saw that coming. And we can show that that's calcium and alumina by using X-ray mapping on the cross section. And you can see the aluminium here in the light color. So it shows the layer of aluminium, high concentration of aluminium, a high concentration of calcium at the interface. So what's happened there? As the carbon's dissolved and the silicon's gone into the hot metal, we've left behind residue of calcium and alumina, and we form these intermediate calcium aluminates. So we form a reaction product at the interface. So increasing the time didn't help here anymore. So there's plenty of examples of these sorts of things happening around the system. Lots of these heterogeneous reactions. The rate limiting processes can change unexpectedly with temperature and the processing conditions. So even if we change the thermodynamic driving force or the temperature, we can get significant changes in reaction mechanism. And that reflects in the reaction rates which take place. So what are we going to do about it? Well, my advice is to make sure you do enough experiments. I'm an experimentalist, basically. And I suggest that before you design in detail your large plant, you make sure you do enough laboratory and pilot scale test work to ensure that you don't get these unexpected and unwanted changes in reaction mechanism as you change the process conditions. That is either the thermodynamic driving force or the temperature. We need to know what's going to happen before we make this large investment in the processing plant. So thanks for listening to the webinar. I'll leave you with a bit of marketing for those of you who are still studying metallurgy. I've just released this book, Process Principles in Minerals and Materials Production. It's available free to students. You can download it from the website there, peterhayesmetallurgy.com. And I hope that you'll pick up some other tips on what's happening in metallurgy. So thank you very much for listening, and I think we're going now to the question and answer. So I'll stop sharing and see where we go from there.
Thank you very much, Professor Hayes, for that inspiring presentation. I enjoyed the practical nature of your presentation. I mean, looking at the evidence and what the evidence is telling us. And I mean, the visual case studies were joy to see, and of course, also highly educational. So let's go to the questions. So the first one, I'll start with the first one from Johann Zitzmann. It seems like the different nickel oxide reduction behaviors at different temperatures may be strongly influenced by surface energy, especially of the nickel metal phase. Are we able to measure that and perhaps ultimately model or predict the behaviors under different conditions?
Yes. So one of the things that's important here about, well, yes, I'll leave the physical metallurgist to measure the surface energy, but what's important in terms of breakdown, I think, is the mismatch between the nickel and the nickel oxide. They're actually the lattice parameters of the nickel metal and nickel oxide are actually very close to each other. So when you get an initial layer, you get a coherent interface, what we call a coherent interface between the nickel and the nickel oxide. So that means the nickel atoms actually match up very well, whether it's oxide or metal. And this gives you quite a strong binding at the interface. However, when the layer gets thicker, then you get mechanical stress built up across the interface, and that helps to break down the interface. And I believe that breakdown occurs where we have some discontinuity. There may be dislocations within the nickel oxide or impurities there, something which will aid the nucleation of basically a gas bubble. And so once you can nucleate the gas bubble, that's when reaction can occur, rapid reaction can occur, and that's where you get those mini volcanoes, which literally blows the surface layer apart. That's my theory, but certainly it's related to the physical properties of the layer.
Many thanks, Prof, for that comprehensive answer. So the next question is a very practical one from Sakile. How can hydrogen be fed in a DRI rotary kiln as a reducing agent to replace coal in the process of producing sponge iron?
So, sorry, can I say that? Can you, it was the question, how can you use hydrogen, did you say?
Yes, how can hydrogen be fed in a DRI rotary kiln? And this is as a reducing agent, and this is really then to replace coal in the process of producing sponge iron. Thanks.
Well, if you're making iron, if you go back to that slide with the iron, oxygen, hydrogen system, what you find is as you increase the temperature, the phase boundary between iron and iron oxide moves to lower concentrations of hydrogen. So you can actually reduce the iron oxide more easily as you increase the temperature with hydrogen in the case of iron. Okay, so you actually get benefit by going to a slightly higher temperature in the case of iron. That's not to say that other things could happen, but from a thermodynamic point of view, it's easier to get to that critical condition where iron will nucleate and form. Hydrogen tends to give a faster reaction rate than CO on these gas-solid reactions, and so the chemical reaction rate should be quite fast. My guess is that in those systems, you're going to be limited much more by mass transfer in the gas phase, either to the reaction interface or through the reaction product.
Okay, thanks, Prof. So the next question is from Jayasri. It's what happens in the case of a mixture of oxides? Can you please comment on selective reduction study?
Yeah, well, so reduction of what oxides, sorry?
So it's looking then in a mixture, so then this will be a mixture of oxides.
Yeah, so So you're reducing a composite material. So the thermodynamic stability of those different phases is going to be different. So you may end up producing, if we're selectively reducing one metal, you may end up with a composite material. So a metal and a non-metal product encapsulated in it. I've seen, for example, I know, for example, in the case of iron oxide with a high concentration of calcium in it, when it's in solid solution, the calcium in the iron oxide to start with, if you then reduce the calcium oxide or the solid solution with magnesium oxide in, you'll selectively reduce the metal to produce metallic iron, and the calcium oxide or the magnesium oxide will not be reduced, and they will form secondary products, which will be encapsulated within the reduced iron. So if you hit it with a high reduction potential, high hydrogen, for example, concentration, you can get porous iron forming rather than the dense iron. And then you get those tunnels forming in the oxide. And as we saw at the example at 700 degrees centigrade in the nickel oxide, you see that the tunnels get their way all the way into the underlying oxide and leave behind pockets of unreduced material. So that's one way of making a composite material by doing that. Whether you want to do that or not, that's your choice.
Thanks, Prof. Your visual answers they're very inspirational. I can actually have a nice picture from your explanation. So the next question is from Julian. In all liquid systems, such as metal, MET, and slag interactions in copper and PGM smelting, would you expect higher temperature to generally suit separation rates?
The liquid systems and liquid solid systems, generally, if we're going to higher temperature, then things like spinel are less stable at the high temperature. So that any reaction between the liquid phase and the spinel would certainly go faster at higher temperature. You're limited there by the reaction, the temperature the reactor wall will stand. So I'd have to look deeply into a specific example. So I can't give you a general answer, but generally things go faster as you go in when you're talking about liquid phase reactions. But I will point to some work by Jeff Belton and Alan Cram, which was done in the 90s, the last century. Their example there, they showed that minor elements can poison the interface. That is, you get selective absorption of surface active elements on the surface of metal. So, for example, if you have iron and you're trying to get rid of the nitrogen from the liquid iron, then if you have oxygen dissolved in the iron as well, the oxygen will form a monolayer or close to a monolayer on the surface of the liquid metal and will slow down the chemical reaction. So that was an interesting one to look up by work by Belton, B-E-L-T-O-N, and also by Cram, C-R-A-M-B. But the other examples, I'd have to look on a case-by-case basis.
Okay, many thanks, Prof. So the next question is from, it's what are your views on activation energy determination using TG analysis versus experimental analysis?
So TGA versus another technique, the technique that I showed you?
Yes, because then so it's the weight loss, of course, from TG versus your experiment.
Well, look, I thought there was an interesting observation that we found that TGA gives you the, if you like, the global change or the integral change in weight, for example. So you assume an average, but it doesn't give you the whole picture of what's actually happening. So I would suggest, if you're going to do that, you do some sort of combination between TGA type of experiments in terms of getting rapid results and an overall picture of what the kinetics are, but then take some of those samples when they've been partially heated up to not to the full temperature, but at different temperatures, stop the TGA and cool them down again, and then cross-section and have a look. I'm sorry, I'm a great fan of mechanisms, and I come from a materials sort of background. So microstructure is everything. It tells you a whole lot of information that you need to know to understand what's really going on. So a combination of techniques I would use.
I fully agree with you, Prof. Many thanks. So I think that ends I don't see any more questions under the Q&A, but of course there are quite a few comments. And we also have a few global specialists in Pyro. So for example, I see a comment here from Lloyd Nelson. Hi, Peter. Very interesting and relevant. Always great to hear your lectures. Good to be reminded again of some of the work similar to Stephanie's thesis work. So that's one of the comments. And of course, I mean, I'm very grateful for the textbook as well. Marcos, for example, he says, many thanks, Prof. I really appreciate the lecture and the textbook. So I think, and again, just a bit of background. I first saw the textbook just about a year ago. And then from there I said, please, I would like to get Prof. Peter Hayes to present a bit, to say a few words about the textbook. And here we are now talking a bit of Pyro, and of course also marketing a bit of your textbook, Prof. Many thanks for that. There's another comment from Lloyd Nelson. The dynamic changes in interfacial tension with the cause of reaction and so impact on reaction rates by Goff Bilton and Alan Graham are indeed classics, as suggested by Prof. Peter Hayes, if you are unaware of them. So again, another great comment there. So Prof, it's a big thank you to you. And of course, I mean, again, I'm a very passionate pyrometallurgist, and from the SAIM side, this is a record. I've shared a bit of pyrometallurgical and metallurgical webinars, and also some mining webinars. But always I've been envious because mining webinars usually bring more attendees. But this time we've had in excess of attendees from all over the globe. So it's a big thanks to you, and of course, many thanks that there's been interest from attendees. And again, there's a comment from David, which is saying then, when is the next presentation? That is, when is the next presentation from you? Because what I see is that there's big potential for another presentation. I mean, I couldn't have enough of this. You could present for the whole day. So, Prof, it's a big thanks to you. And again, a big thanks also to the team from OZIM for making this collaboration possible. I mean, this is showing that this is a huge success. So we would like to continue collaborating between the SAIM and the OZIM. Maybe then also before your last words, Prof, maybe Stuart, would you also like to say some words from the OZIM side?
Yes, so from the OZIM side, thank you very much for the talk today, Peter. It was fantastic. Having done a lot of work on kinetics, I always enjoy listening to lots of kinetic talk, so that makes my day happy. And thanks again, Peter, for the talk and setting up some collaboration between SAIM and the OZIM. So we'll hope we'll be able to do some more collaborative talks in the future. And I believe it's the OZIM's turn to host the next one. So we'll probably be organizing a talk and advertising that both within the OZIM as well as SAIM. So I'm looking forward to doing some more collaboration between the two.
Thanks, Stuart. And Prof, maybe the last words from your side?
Yes, again, thanks very much for the respective institutions from South Africa and Australia. So it's good to get people together despite the difficulties we have with traveling and meeting each other in person. But I think at least it takes one step towards breaking down those barriers and sharing our common knowledge so we can all understand things a bit better. So I didn't want to plug too much, but the commercial, but if you have colleagues who would be interested in reading the textbook, as I say, it's available for students, it is free and it's by donation. So I'm just marketing this myself. So please, it's word of mouth. I don't mind how many people read it, as many as possible. If we can get more people doing metallurgical engineering, the better.
Absolutely, Prof. Thanks once again for sharing your wisdom. And this concludes the webinar. Cheers, everyone.
Goodbye. Thank you.
Thank you, Prof. Hayes. Bye-bye.